Three things are certain in life: death, taxes, and the difficulty of factoring large numbers. But in this episode of Qiskit in the Classroom, we'll explain how Shor's algorithm may one day shatter that last certainty. In the early 1990s, there was growing excitement around the potential for quantum computers to solve problems that were hard for classical computers. But nobody had yet found a single killer app that was sure to revolutionize the field. That changed in 1994 when Peter Shor came up with a method to factor large numbers exponentially faster than any classical computer could. This might sound like a niche problem that only mathematicians would care about, but our entire digital lives rests on the assumption that factoring large numbers is hard. Your bank transactions, private messages, the secure connection between your browser and every website you visit. The encryption protecting all of this is built on the bet that nobody can efficiently break a large number into its prime factors. Shor's algorithm is a direct challenge to that bet. Now, there's an important caveat. Shor did this by offloading the hardest part of the problem onto a quantum computer, a machine that didn't exist in 1994, and that still doesn't exist at the scale that we need to break real encryption. Even after 30 years of remarkable progress, we're not there yet. But that's not the point. Shor's algorithm matters because it changed what we thought was possible. It was the moment quantum computing went from a physicist's curiosity to something the world had to take seriously. And we fully expect that one day, with error correction and larger qubit counts, we will be able to run it at scale. In this episode, we'll explore how it works. First, we'll dig into the problem and why it sits at the heart of modern cybersecurity. Then we'll uncover the hidden symmetries in the factoring problem, the cyclic structure buried in the problem that Shor had the brilliance to exploit. We'll walk through the full algorithm, explaining exactly which steps need a quantum computer and why. And finally, we'll run a demo on a real quantum computer to factor the number 15. As difficult as it is to solve the factoring problem, the problem itself is conceptually very simple. Given a composite number n, which is p times q, find the prime factors p and q. That's it. The difficulty might seem counterintuitive. After all, doing the reverse, multiplying p and q together, is trivial. But multiplication is a one-way street. It takes two numbers and scrambles them into one. Factoring requires untangling that scrambled information. All known classical algorithms are hopelessly inefficient at this. The time required grows exponentially with the size of n. This asymmetry is exactly what modern public key cryptography is built on. In RSA, two large primes are multiplied to produce n, which becomes part of the public key, the lock that anyone can use to encrypt data sent to you. Decrypting it requires knowing p and q, the private key. The whole system works because even if you know n, finding p and q would require millions of processor cores running for years, a scale of resources that has never been worth anyone's while. And cryptographers are already quietly moving to even larger key sizes just to stay ahead. This is where Shor's algorithm comes in. Shor's insight relied on the relationship between the factoring problem and modular arithmetic. If you haven't heard of modular arithmetic before, that's okay. I'm guessing you already know how to do it, even if you don't know that you know. The way we keep track of time is an example of a modular system. Whenever you set your alarm for the next morning and calculate how many hours of sleep you'll get, you're performing modular addition, because time winds around like the hands of a clock, repeating itself every 24 hours. Obviously, the clocks we all use have 12 hours on their face, but the AM-PM distinction effectively makes this a modulo 24 system. We can apply this clock analogy to any modulo n system, where n is the number of positions on the clock face. We say two numbers are congruent modulo n if they land on the same position. In other words, if they're indistinguishable on that clock. For example, 26 is congruent to 2 mod 24, and 16 is congruent to 1 mod 15. Modular arithmetic supports all the same operations you're used to: addition, subtraction, multiplication, and, importantly for us, exponentiation, raising a number a to the power k modulo n. Let's see how this works in an example. First, without the modular part, if we plot 2 to the k as a function of k, we get this. To instead plot 2 to the k modulo 15, we can slice up the graph into sections of 15 and collapse them all on top of one another so that every point lands in the range from 0 to 14. Then we get a graph that looks like this. And if we extend to higher values of k, we see that it's a periodic function. Let's look at this plot for other values of a. Now, looking at all these graphs, you might notice two distinct types of behavior. They all start at 1, but some never return to 1. This happens when a and n share a common factor. For example, if a equals 6 and n equals 15, they're both evenly divided by 3. The purely periodic ones, the ones that regularly return to 1, are those where a and n share no common factors other than 1. We call this being relatively prime, and we write it as GCD of a n equals 1, where GCD stands for greatest common divisor, the largest number that divides evenly into both. All the numbers a for which GCD of n and a equals 1, together with the multiplication operation, form what mathematicians call a group. And everything about that group, from its size to its rich substructure, is entirely determined by the factors of n, p and q. Shor's algorithm uncovers the factors by analyzing these periodic functions, each of which represents a different cyclic subgroup within the larger group. Specifically, Shor's algorithm finds the period, or the order, which is the value of k at which the function first returns to 1. We define the order r as the smallest positive integer such that a to the r is congruent to 1 mod n. To show exactly how finding this order reveals p and q, we need to do a little math. It might not be obvious where we're going at first, but I promise it'll make sense in the end. Let's start with the number x, whose square is congruent to 1 mod n. So x squared is congruent to 1 mod n, but where x itself is not congruent to either plus or minus 1 mod n. For example, if n equals 15, then x equals 4 satisfies both conditions. 4 squared is 16, which is congruent to 1 mod 15, but 4 is not congruent to either plus or minus mod 15. Now, subtracting 1 from both sides of the first equation gives us x squared minus 1 is congruent to 0 mod n, which just means x squared minus 1 is a multiple of n. So we can write that as L times n for some integer L. Factoring the left side, we get x plus 1 times x minus 1 equals L times n. And we can write n as p times q. Now here's the key. We know from our condition here that neither x plus 1 nor x minus 1 is itself a multiple of n. That means p and q can't both be hiding in the same factor. They must be split across the two. One divides into x plus 1, the other into x minus 1. And if that's true, then taking the greatest common divisors yields the factors. GCD of n and x plus 1 equals p. GCD of n and x minus 1 equals q, or vice versa. So, finding the prime factors of n simply comes down to finding an x satisfying these two conditions, then computing two GCDs. And here's where we all bring it back to the order finding. If we take a number a, find its order modulo n, and that order happens to be an even number, then we can set a to the r to be x squared. And then x will be a to the r over 2. Then we can find p and q by just calculating the GCD between n and a to the r over 2 plus or minus 1. Shor's algorithm is exactly that process I just outlined. Pick a random integer a and compute the GCD between a and n. If the GCD is greater than 1, then lucky you already found a prime factor. But if the GCD is 1, which is more likely than not, you then go to this next step. Find the order r of a mod n. If r is odd, then we have to start again. We have to pick a new a. If r is even, then we can continue. We compute x, which equals a to the r over 2. And we make sure that x is not congruent to minus 1 mod n. If it's not, we can continue, but if it is, we have to go back to the top and pick a new a. So if it's not congruent to minus 1 mod n, we can then compute the GCD between x plus and minus 1 and n. And if those are prime, then we're done. We found the prime factors. If they're not prime, then we can apply this same procedure recursively until all of the factors are prime. Remember that RSA only uses products of 2 primes, so we only need to do this once for that application. Based on this procedure, it might not be obvious exactly where a quantum computer will help us. It's necessary because of this step here. Finding the order of a modulo n is classically a very difficult problem. The complexity scales exponentially in the number n. We say that the factoring problem reduces to the order finding problem, meaning that every other step is trivially easy compared to order finding. But with a quantum computer, the order finding problem actually becomes tractable. Remember what the order is. It's essentially the period of these modular functions. Quantum computers are extremely well suited to finding the period of functions. For this, we can use an algorithmic subroutine called quantum phase estimation, or QPE. We discussed QPE and its relationship to the quantum Fourier transform in a previous video, so if you haven't watched that, I suggest you pause this video and watch it now. But if you want a brief refresher, I can give you the basics. In quantum phase estimation, we start with a unitary u and an eigenstate of that unitary psi. Then we use quantum phase estimation to approximate the corresponding eigenvalue, which, since the operator is unitary, will be of the form e to the 2 pi I theta. So, finding the eigenvalue is equivalent to finding the value of theta in the periodic function. The circuit looks like this, where these bottom qubits are initialized to the state psi, and the number of control qubits at the top determines the precision of the approximation. In Shor's algorithm, we can use quantum phase estimation on a unitary operator m sub a, which transforms a state y like this. Here, y denotes a computational basis state, where the binary value of the qubits correspond to the integer y. For instance, if n equals 15 and y equals 2, then y is represented by the 4-qubit basis state 0, 0, 1, 0, since 4 qubits are required to encode numbers up to 15. Now we need to figure out an eigenstate of this unitary. If we started in the state 1, we can see that each successive application of m will multiply the state of our register by a mod n, and after r applications, we'll arrive back at the state 1, remembering that r is the order of the function. So, for example, with a equals 2 and n equals 15, m sub 2 times 1 equals 2, m sub 2 times 2 equals 4, m sub 2 times 4 equals 8. M sub 2 times 8 is 16 mod 15, so we go back to 1. So after 4 applications, we're back where we started. So we know the order of 2 mod 15 is 4. It turns out that superpositions of these 4 states, weighted by complex phases of this form, are eigenstates of M sub 2. If we could prepare one of these states, QPE would give us its eigenvalue e to the 2 pi I j over 4, from which we could read off j over 4 and determine r equals 4 directly. But here's the catch. Preparing any one of these eigenstates requires knowing r. It might seem like we're stuck. We need to know what r is in order to find r. But we can use a trick to get us unstuck. It turns out that the state 1 is itself an equal superposition of all 4 of these eigenstates. So instead of preparing a single eigenstate, we just start in 1. Then, when we run QPE, we'll get an approximation to j over r for some random j. With enough measurements, we can piece together r. Now we're ready to see how this is done in practice on a real quantum computer. Let's factor 15, choosing a equals 2 to be our coprime integer. First, we need to construct the circuit that will implement the modular multiplication. This is actually the trickiest part of the whole implementation and can be very computationally expensive depending on how it's done. For this, we'll cheat a little bit. We know that we're starting in the state 1, and from an earlier example, we know how the application of M2 cycles through the states. To keep things manageable, we'll construct a simplified unitary that correctly implements modular multiplication on these 4 states by just permuting them in the right order. This works for our demonstration, but we're using prior knowledge of the order of 2 mod 15 to hard code the answer into the circuit. A fully general implementation would have to build modular exponentiation from the ground up, which would require far more qubits and far more gates. For the purposes of this demo, the shortcut is fine, but it's worth knowing that this is where the real engineering challenge lives in any practical implementation of Shor's algorithm. Here's where we define the M2 operator, which ends up just being a series of swap gates, each of which decompose into 3 C-naughts, as you can see here. Then we need to make this a controlled M operator, so we introduce a control qubit and adjust the circuit accordingly. Finally, the last gate we'll need for the quantum phase estimation is a controlled M4 unitary, which is the square of M2. So we do the same thing as before. We have our M4 gate, then we make it a controlled M4 gate. And now we can put it all together to find the order of A mod n. We have our control qubits on top. And remember, the more of these we use, the more precise our phase estimation will be. Then these qubits, labeled T, are the ones that encode the integer and have the modular multiplication gates applied to them. We apply this X gate here to start in the state 1, then proceed with quantum phase estimation. And after we optimize and then execute this on our quantum computer, here's our histogram. We see 4 clear peaks here, 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 and here, with some counts in other bit strings due to noise on the quantum computer. Now remember, only the order finding part of the factoring procedure is completed on the quantum computer itself, so we still have some classical computing work to do to extract the factors from what the quantum computer returned. This code goes through each shot from the quantum computer one by one and tries to find a factor from the measured bit string. Not every shot will be useful, but in our case, our first attempt, we got lucky and found a non-trivial factor of 3. Just divide 15 by 3 to find the other factor, and we're done. So that's it. Shor's algorithm demystified. It may make sense when you work through it step by step, but I still find it incredible that Shor had the insight to see all of this in the first place. We're all lucky he did. This single algorithm broke open the floodgates of quantum computing as a serious field, and the clever algorithms that followed wouldn't exist without it. While we're still far from using this to factor the numbers actually used in RSA, our quantum computers are getting better every day. Once a threshold called fault tolerance is reached, algorithms like this will be close behind. But don't worry, that doesn't mean internet security as we know it will cease to exist. It just means we'll need cryptographic methods that are secure enough against quantum computers. Fortunately, that work is already well underway. NIST finalized its first post-quantum cryptographic standards in 2024, and researchers at IBM and elsewhere have been developing quantum-safe protocols for years. Make sure you check out the module on the IBM Quantum platform to run Shor's algorithm yourself. See you next time.